So we now have a new state function, entropy, and remind you it's defined in this way that differential change in this new state function would look like an incremental change in reversible heat divided by temperature. All right, so we want to use this now in a practical problem-solving example so you can see exactly how one might evaluate it. All right, so this is just an illustration. So let's suppose that we have a constant pressure process. All right, what this means is that our increment of change in heat that's reversible is really going to be an incremental change in heat at constant pressure. All right, and we could make sure that we're doing this in such a way that even though it's constant pressure, that it's done in a reversible manner. Now we also know from our earlier work that this could be written as the constant pressure heat capacity times a differential in temperature. I'll also remind you that this quantity here, this differential change in an incremental change in heat, is equivalent to our differential for this state function enthalpy. So what we want to do is we want to evaluate our entropy change for a constant pressure process. Now to get a handle on this, let's draw a little PV diagram just to make sure we've got it visualized. So we're going from a point 1 to a point 2 along this, and this is really characterized by V1 and V2, these molar volumes along the way. So now when we set up our evaluation of the change in entropy, we're going to be integrating from point 1 to point 2 along this path. Now I'll also point out that even though we're focusing on the change in the volume, that we're also moving from one isotherm to another. So we also have a change in temperature that's going to go from temperature 1 to temperature 2. So we're going to do that first, and then we'll convert back to the volumes after we're done. So now when I write down the expression for my differential change in entropy from there, it's going to be an integration from point 1 to 2 of our constant pressure heat differential divided by temperature. And now I've seen that this can be equal to this, but I'm going to be doing it from temperature 1 to temperature 2, Cp dt over T. All right, we're going to assume that the constant pressure heat capacity is relatively constant for this process, so we'll bring it outside the integral, and that means we have again this really simple form of an integral that just gives us Cp log of T2 over T1. All right, now I said we were going to change this to volume. Well, we know from the ideal gas equation of state that pressure times the molar volume is equal to RT. So if I want to change T to volume, I'm going to have to solve for T here. So it means that T1 is going to be pressure over the ideal constant times molar volume 1, and T2 will be equal to P over R times molar volume 2. So now if I want to calculate T2 over T1, that's going to be just to substitute these two values in for those two quantities. I'll have P over R molar volume V2 in the numerator and P over R molar volume 1 in the denominator. I think it's easy to see that the pressure and the gas constant are both going to cancel in this, and we'll end up just having the ratio of molar volume 1 over molar volume 2 over molar volume 1. So that means that in the end, our final result over here, which is equal to the change in entropy, can simply be written as Cp times the log of the ratio of the two molar volumes. So that gives you an idea of how one might evaluate the entropy change for a given process, something like this.